Now we're going to get the last type of volume, which is another volume by revolution, except this one's going to end up having not a perpendicular cross section. Remember, last time, let's say we're going to revolve this around the y-axis. If I have a perpendicular slice, you generate either a solid disk, or if that slice would have had the empty space, then you would get the washer with the hole. So perpendicular slices gave us the solid disks or the washers with the hole. But like, what happens if we have a parallel slice? What happens if my axis and my slice are actually in the same orientation? Well, what's going to happen is that top point's going to revolve around, that bottom point's going to revolve around, and instead of getting a solid circular disc or a washer with a hole, instead of getting anything like that, we're actually going to get this thing called a shell. And it looks like a cylinder. Now it's going to be hollow. It's really only the edge of the cylinder and then the outside lateral area of it. It's hollow, right? It's like a toilet paper roll or a paper towel roll, right? And we're just really basically trying to figure out, like, what's the volume of that cardboard used in that specific toilet paper roll, for instance. And so here, if we take that one slice and we revolve it, top goes around, bottom goes around, that parallel slice gives us a cylindrical shell. And that shell, if we were to think about taking a pair of scissors and then cutting it and unraveling it, that shell would unravel and it would be a rectangular prism. I think about taking a toilet paper roll, cutting it, and then the length of this rectangular prism, that length would have been the circumference of the cylinder, which we know is 2 pi r. So the length of this solid is the circumference, so long, the circumference of the cylinder. There we go. I can spell occasionally. And that one's going to be 2 pi r, right? That's the formula for the circumference. And then the height of this solid, well, that's just the height of the cylinder. Okay, that doesn't really change. That's still just going to end up being the height of the cylinder. I'm going to abbreviate it. So h. And then now let's think about that third dimension, because if we only have a width and a height, well, that's 2 dimensions. That's an area. That third dimension, that's like the width. That's like the thickness. And what that comes from, right? If you think about your toilet paper roll, that's like the thickness of that toilet paper roll, which comes from the dx, right? Or which comes from that thickness of the cylinder. So I guess we can think about it like this: the thickness of the cylinder, which for us is going to end up being the delta x, which later on, as it becomes infinitely thin, will be the dx. But if we were to take that one slice that's parallel to my axis of revolution, and if I were to revolve it, the top point revolves around, the bottom point revolves around, we end up with this cylindrical shell. We don't want the whole cylinder. We don't want the volume of it. We really just want the lateral area of it. And then we're going to integrate the area to get the volume. Really, right? Except now it's just not the area of a circle or the area of a washer. It's now the lateral area of this cylinder. Right? It's all that edge, but it's a hollow cylinder. And so here we go. If I were to find the volume of this cylinder, we would have 2 pi r, right? We'd take this times this times this. So 2 pi r, that's the length, the circumference, times h, and then times that little thickness. Come on, smartboard. Times the little thickness, the delta x. But we know that's just the volume of one little arbitrary cylinder, or one little arbitrary cylindrical shell, I should say. And we know we would want to somehow compile all of them. Like, I wouldn't want just that one cylinder. I would want this one too. Right? I'd want the one that's right there. And that one may be a little bit narrower, but I would want that cylindrical shell. And I would want all of these other ones too. Let me draw a couple because it's fun. I would want this one, which when you revolve it, is going to give you your cylindrical shell. And then I'd want this one over here, which when you revolve it, top goes around, bottom goes around, gives you the cylindrical shell. Right? And really, instead of building these things, right, instead of having things build from the bottom to the top, which when you revolve them, like, could be washers, or they could be discs. That's the word I was looking for. Instead of building things either from the bottom up or from the left right, now we're really building it from the inside out. Whenever we have this 3D volume, right, this figure that's going to be created, we're really building it from the inside out. And we're starting with that closest slice. And when you revolve that closest slice, that's like kind of the core. And really, since that region is flush up against the axis of revolution, that closest slice is just 0. But then you would build it from the inside out. And I would take the slice right next to it. And then that's going to give me the shell right around that core. And then I would just keep going. Then I would take the next one. And then that shell would kind of be nested outside, right? And we're really going to be building it from that inside out. And then eventually, right, we keep working. That point revolves around. Then we have that shell, and then we have this one, right? We really want all of these nested shells all within each other, starting with the innermost one and then ending over here with that outermost one. I kind of made that one was terrible. I'm going to read that one. Top point revolves around, bottom point revolves around. Here we go. So instead of building it from the bottom up or from the left right, we're really building it from the inside out. But each one of these little things that we're going to have to accumulate, each one is the lateral area of a cylindrical shell, right? And then we're going to add all infinitely many of them together, but that's what integration does for us. Here's the formula, right? Key takeaway. Again, we're going to integrate the area to get the volume, but the area is now the lateral area of a cylinder. So we're going to have 2 pi, then we're going to integrate r h, 2 pi RH. That is the area formula for your lateral area, right? 2 pi RH. But we're going to have to get the radius to be in terms of x and the height to be in terms of x. Right? If this is a dx integral, I need x equals a the left to x equals b the right, and then we'll have 2 pi RH. That's the area that we're now integrating. Integrate the area to get the volume. That's still the same thing, but now when we have this parallel axis, and I revolve it around my parallel slice to my axis of revolution, we actually have these cylindrical shells that we have to compile. So 2 pi, and then I'm going to integrate RH. Now, if this is a dy integration, of course, it's going to be from C to D, from the bottom to the top, and then you would need both your radius and your height. You need them to be defined by y's. So pi r squared is disk. Pi big R squared minus little r squared, that's washers. 2 pi RH is shells. And really, disks and washers are kind of like one method, and then the shell is like the counterpart, right? The disks and the washers, that's the perpendicular slice, and then the shell is kind of the corresponding parallel slice. One of them will be the dx, and then the other one would be the dy. For instance, if we had this axis of revolution was the y-axis, well then if I have a horizontal slice, so that would be a dy integral, that would end up being the disks. Now, it could be disks or washers, right? They're kind of the same thing. A disk is just the easiest type of a washer where the little radius is 0. But there, the dy integration would be the solid disks, and then here the dx would end up being the washers. Right, so here, sorry, not the washers, this would end up being the shells. So that was the disks, and then the other one would be the shells. Now, if we were to do something different, like how about if I were to take that region, let me just kind of sketch it again. If we were to take this region, and if we were to revolve it now around, how about the x-axis, which would be different. What would happen if we took that and we revolved it around the x-axis? Well, if I had a horizontal slice, right, that's still the dy, so right, it's kind of the same setup. But now if I have a horizontal slice and a horizontal axis, now the dy is going to end up being the shells. And then if I did a vertical slice, just like I did over there, if I did a vertical slice, now that's perpendicular. So now that dx, that would end up being the disk. And it could be disk or it could be washers. But they're kind of these counterparts for each other. The disk and the washer is going to be one method, either the dx or the dy. And then the shells will be the other one. We can pretty much always do either dx or dy, but one of them will be the washers and the other one will be the shells. So it's kind of nice to know both. Now, an important note, the AP exam is not going to ask you about shells. Right? It's going to pretty much always want you to do solid disks or to do washers. But I think it's nice knowing how to do the shell method also. Because if you don't know it, you're kind of like just going through without having your full armada of tools, right? It's nice. For area, we can always do dx or dy. Sometimes one is easier than the other, but we can always do either. Same thing is true for the volume. We can always do dx or always do dy, but for these volumes of revolution, if the washer is dx, then if I wanted to do dy, I would have shells instead, or vice versa. I guess the cross-sectional ones you can't really choose. You just have to do, right? Because it tells you perpendicular to x, which means dx, perpendicular to y, which means dy. But for the volumes of revolution, we can choose to either do dx or dy. One of them will be washers or discs, right? That's just the easiest type of a washer. And then the other one will be shells. Here we go. So what's the process for finding these shell method problems? First thing we do is we read the question and we determine whether we're going to use dx or dy. Now, what you have to remember is that the shell method, there I go, moving it again and not using the pen, the shell method, that's the only one where we want a parallel slice. Now, it's kind of nice, right? Shell, you got the two L's, parallel, you got the two L's, and remember, the two L's in shell and in parallel, they are parallel, right? So shell, parallel, everything else is perpendicular. For the cross-sectional stuff we did a couple times ago, it was always perpendicular. Perpendicular to x meant dx, perpendicular to y meant dy, right? That was easy. But for the discs and washers, we always wanted it to be perpendicular. Shell is the corresponding equivalent for when we have a parallel slice. Shell is parallel, perpendicular is disc or washer. Okay, so here we go. The first thing is to read the question and to decide, do we want dx or do we want dy? The second thing is, if it's a shell method, I know I have to integrate 2 pi rh, so I have to identify what's the r and what's the h. And then I need to get them both, either in terms of x for a dx integral or into y for a dy integral. So identify which methodology, dx or dy, and then identify the r and the h, get them in the correct variable, and then, of course, integrate the area to get the volume. But now it's the lateral area of that cylindrical shell, 2 pi rh. That's what we're integrating. All right, let's go through and let's do some examples. I think we got just a couple pages, and then we'll see. Okay, here we go. Set up the integral expression that can be used to find the volume when the region bounded by y equals x squared plus 1 and y equals 0 is rotated around the given axis. And it specifically tells us, notice, it tells us to use shells. If the question doesn't say do discs or do washers or do shells, if it doesn't tell me exactly what type to do, then I can choose. But if it tells me to do shells and I do washers, that's a problem. Or if it tells me to do discs and I do shells, that's a problem, right? If it tells you specifically to do one type and you do it different, that's a problem. If it doesn't specify, you can use either, right? You can use any strategy that makes you feel more warm and fuzzy. But here it tells us to do shells. All right, let's graph them. This parabola shifted up 1 unit. Here we go. Do it over here too. And it says the parabola and y equals 0. That's the x-axis. I just love saying y equals 0. So there we go. There's the x-axis, y equals 0. It's kind of nice because you have y equals, y equals. That's easier than when it says x-axis, which you then have to remember is y equals. And it says, hey, that region, there's nothing naturally inherently bounded between those things because they don't intersect. But it says, hey, we're going to have the region bounded by those over the interval 0 to 2. So really, x equals 0 is the left, and then x equals 2 is the right. So here we go. There's the left side, and then 1, 2, there's the right side. May not be perfectly to scale, whatever. 1, 2. So 0 to 2, that's kind of our other sides. Come on, you can do it. There we go. All right, let's fill this sucker in. There we go. There's our region. I've decided, apparently, that yellow is just always going to be my fill color. All right, now it says my axis of revolution for this first one is the y-axis. So there we go, the y-axis. And then for the second one, we've got x equals -1, which is going to end up being over here on the left. Okay, so x equals -1, and of course that one's going to be x equals 0. Now, if we want shells, remember my cross-sectional slice has to be parallel to it. My little arbitrary slice has to be parallel to it. So here we go. If my axis is vertical, that means my little slice is going to have to be vertical, which means this is going to have to be a dx integral. That's just an arbitrary xy point. And then let's swing this guy around. The top guy revolves, bottom guy revolves. That wasn't very good. What's nice about the smartboard is I can kind of erase it and then eventually get one that's passable. But I take that one arbitrary slice, bam, now I got my one shell. And I need to get the area, the lateral area of that one shell, and then I'm going to integrate the area to get the bottom. Okay, let's figure out what these two dimensions are. Remember, for the shell, we're going to have an R, we're going to have an H. Here's the radius. The radius is the distance from my axis of revolution to that slice. Remember, the slices are parallel, right? So you're not going to have to do the distance to the closer point or the farther point. They're going to be the same distance. Okay, so that radius is the distance from the axis of revolution to that slice. And here, that distance is horizontal. So here, the radius is going to be x. And it's a dx integral, so I don't have to change it, right? It wants it to be in terms of x, so that's very good. And then the other part, right, 2 pi rh, I need to know what is the height of the cylinder. But the height is the length of that slice. It's the vertical distance of that cylinder. And so the height now is going to be the y value. One of them is going to be a horizontal measurement. The other one's going to be a vertical, right? Whenever you have a cylinder, one of the dimensions is going to be sideways, the other one's going to be up and down. So one of them will be in terms of x, and the other will be in terms of y. That's kind of good news, bad news. The good news is that one of them is going to already be in the correct variable, which for here, that one was. And then the kind of bad news is that means the other one is always going to be in the wrong variable. So I'm going to have to switch it. But I know what y is, right? Y is just the curve x squared plus 1. So 2 pi rh, that's the formula we have to integrate. I sketch the graph so that I can visualize what's the radius, what's the height, make sure I get them into the correct variable, and then here we go, we're ready. Let's just throw it all together. Let's get this integral done. Here we go. Volume equals 2 pi, and then we're going to have r, h. This was a dx integral. And then here, we're going to compile all of these slices, starting with the first one over here at 0, and then all the way to this last slice. And then that one was 2, right? It was 0 to 2. That was our parameters for this integral. Okay, and that would be a perfectly good answer. You don't necessarily have to do anything else if you wanted to. Since that one's pretty easy to simplify, you could, we'd have the 2 pi 0 to 2, you could have x cubed plus x. Like that would be the same thing. Like that's an equally correct integral, but it doesn't matter, right? You could leave it as the r times h, or if you want to multiply it out, that's fine. Either one of those is correct. All right. And again, if you have to get the volume, you would probably have a calculator. Could we integrate that? Yeah, that's a pretty easy integral. It's not super complicated. Plugging in 2 would be easy. Plugging in 0 would be even easier. But if we had to do it by hand, we would just have to leave it in terms of pi. But typically the questions, if it's non-calc, are going to just have you set up the integral, and then if it actually wants to get the volume, you will likely have a calculator and then TMath 9 it to get that decimal. All right, next one. Let's look at it. Now we've got a different axis of revolution, but x equals -1, that's still vertical. And since I need a parallel slice, that means I'm still going to need a vertical slice. So this is still going to be dx. Now, when I take this slice, the top point revolves around, bottom point revolves around. And so there we go. There's my cylindrical shell. Let's go think about it. The height. The height is, again, still just going to be that y value. Remember, that's an arbitrary x and a y point that's on the purple function. So that vertical distance, the height, that's just the y value. And then here, this radius, right? This horizontal distance from the or from that y-axis, from the y-axis over to my slice, that distance is x. This distance is 1. So what's this whole radius going to be? X plus 1. Okay, but the radius was horizontal, but it wasn't just x, because you didn't just have to get to the 0. You had to actually go to 0, the axis, and you had to go 1 unit farther. Right? If it would have been at x equals -5, the radius would have been x plus 5, because you would have had that width of 5 over there on the left side of the y-axis. But the height was still y, so that was pretty easy. All right, now we're pretty much ready. 2 pi rh, that's the formula. And let's just integrate the area to get the volume. Here we go. Volume equals 2 pi rh. The r was x plus 1. The h, ooh, remember, instead of y, we would want to change it. Instead of y, let's change it in the y equals x squared plus 1. There we go. X squared plus 1. So 2 pi RH, that was a dx integral. Now here's the thing that students are going to kind of mess up on. A really common mistake is for students to do -1 to 2. But you have to think, do I really have all of these slices, and therefore do I have these ensuing shells from -1 all the way to 2? No, you don't have any shells for this region, right? Because my region does not exist there. Remember, the yellow kind of diagonal, kind of shaded in region, that's where my shells are coming from. And the leftmost side is still right here at 0, right? The slices come from where your region is. The fact that my axis is to the left of it doesn't matter, right? So here the limit for your integration, it's not -1 to 2, it's still 0 to 2. That's still the left side of the region to the right side of the region. You don't have any slices here, right? So you don't need -1 to 0. You just need the slices from 1 to 2, just like we did on the previous. The fact that that axis has moved a little bit farther, right? That changes something, but that changes this. It does not change the lower limit. All right, so just be careful. All right, but that would be the integral. You could FOIL it out if you wanted to simplify it, but otherwise, it's really not going to simplify very well. Okay, let's do this next one. It says, same idea. Let's set up the integral expression. We have a different curve now. Okay, let's set it up. So I've got the square root function. Do that in purple. Here we go. Square root function. I'll do it in purple again. And then let's do, sure, why not? Let's use the green. Y equals 0. Again, that's the x-axis. And then let's do, sure, blue for x equals 4. There we go. So we've got this region. Again, yellow is my universal fill color. I guess I just decided it, but it's happening now. So there's my region. Let's go get the intersection points just really quickly, just in case we need them, which we will. This intersection point is, of course, the origin. That's 0, 0. And that's, remember, that's the square root function. This is x equals 4. The square root of 4 is 2. So that's the point 4, 2. All right, so this is going to be the point 4, 2. And then again, that is at the origin, 0, 0. All right, so we're good. Let's go now do these axes of revolution. First one, we're going to do x equals 7. Is that on the top, the bottom, the left, or the right of my region? Well, x equals is a vertical line, and then x equals 7, that's going to be to the right. So there's x equals 7. That's vertical, which again means I'm going to have a parallel slice. So I'm going to have a dx integral. Always have to have, right? It told me to use shells. That means I needed a parallel slice. And since my axis was vertical, my slice has to be vertical. So here we go. Top part revolves around, bottom part revolves around. There we go. We've got that pretty big cylindrical shell. And then we have to figure out what's the radius of it and what's the height of it. But again, that point, that was just an arbitrary x, y point. And so let's now figure out what is the r, what is the h, and then we'll set it up. I'm actually going to erase some of this stuff just so I have some room. See if I can erase this without getting rid of the whole page, which sometimes it just doesn't want to cooperate. Okay, let's see. Cool beans. There we go. So let's identify what these two things are. Let's do the height first, because that's easier. Okay, the height. That's just the vertical distance. Remember, the height is really just the length of the slice. The height is the y value. But since this is a dx integral, I don't want the y value, so I'm going to use the root of x instead. Okay, so that one's done. It started off in the wrong variable, but I switched it. Very good. Now let's do the radius. Okay, the radius is this distance right here, from my slice to the axis of revolution. Now, this whole distance is 7. And then this distance right here, from 0, from the y-axis to the slice, that distance is x. So the whole thing is 7. The piece on the left is x. The piece on the right is r. So here I'm going to have to use subtraction. That radius is actually 7 minus x. And it's already in terms of the correct variable. It's a dx integral, so I want everything defined by x. And there we go, we got it. And once I've got the r and the h, we're ready to just bring this together. Remember, 2 pi, that's what goes out in front. 2 pi r, 7 minus x, and then h. By the way, because of the commutative property, it doesn't matter. Like you could flip those two, it doesn't matter. But 2 pi r h, it doesn't matter which one you write first. And then the last thing is, what limits for the integral do we need? Where are these slices going to come from that generate the cylindrical shells? Well, they come from the region. We'd have all those shells starting with that first one at 0 all the way to the last one at 4. I do not go past 4. There's no slices between 4 and 7 because your region stops at 4. So from 0 to 4. There is the integral setup that would represent the volume generated by revolving that square root curve around the the axis x equals 7. I was thinking y-axis. Okay, so there we go. Very good. Let's do this last one, and then we'll kind of scroll it down, and then we actually have 2 more examples. I'm going to kind of erase this just so it's out of the way. There we go. You really don't need to draw the whole cylinder. You just need half of it so you can identify the radius and the height. All right, here we go. Let's do this last one. We've got now our axis is going to be y equals 5. Is that above, below, to the right, or to the left? Y equals is horizontal. Y equals 5. That's going to be above. It doesn't have to be super to scale, but I'm just going to put it up here. Y equals 5. Since that is horizontal, remember, shell method, shell, parallel. Shell needs a parallel slice. So now I'm going to need a horizontal slice. So this is going to be our first shell that needs a dy integration. I'm going to get this previous one out of there because it's going to interfere with my super awesome drawing skills. But if you need to write down that answer, remember, just rewind the video, whatever. So let's take this horizontal slice and let's revolve it around that horizontal axis of revolution. This is going to be like a cylinder, but tipped over on its side. Here we go. That point is going to revolve around the axis of revolution. I always find these are harder to draw. I'm going to erase the 4 too because I think that's going to make it uglier. And then the other point, I lost my orange. Oh no, there we go. And the other point is going to revolve around. And then there we go. I always find the horizontal ones end up slightly uglier. The vertical ones are pretty ugly. The horizontal ones are uglier. But there we go. Remember, that's just an arbitrary xy point. And we need to now figure out what are the 2 dimensions of this cylinder. Here's the radius, right? The radius is the distance from the axis of revolution to where that parallel slice was. So there's my radius. Now that one's going to be vertical. And then here is your height. And the height is still the length of that slice. And then I know I'm going to integrate 2 pi rh, but I need to figure out what's the r and then what's the h. And then once I've got those 2 things, make sure I get them into the correct variable, and then we can go on our way. Let's do the radius first. Might as well. This whole distance was 5. Remember, the horizontal line was up at 5, so that whole distance is 5. This vertical distance is y, so therefore my radius is going to be 5 minus y. Do I need to switch the y into the square root of x? No, because this is a dy integration. So actually, that's the correct variable. That's the one that's correct off the get-go. That means when I find the h, I'm going to have to do some switching. Okay, so this whole distance right here, remember that whole distance, that right side was at 4, I think. That whole thing is 4. This little distance, right, from the y-axis over to this point, that little distance is x. So now here, my height, which is this length of the slice, that's going to be 4 minus x. And I do not want it to stay as x. I need to go back to this equation, and if y was equal to the root of x, I need to solve that for x. So x is going to be equal to y squared. Then I would change it over, and I got 4 minus y squared. Now it's in the correct variable. One of them is going to automatically, at first, be in the correct variable. The other one's going to be wrong, right? Whether you have a vertical cylinder or a horizontal one of those dimensions, since they're perpendicular, one of those dimensions will be in terms of x, the other one will be in terms of y. That means one of them is going to be good to begin with, and the other one you're going to have to change. Regardless of if it's a dx or dy, that's just going to change which one you have to swap. But there we go. We've got the r and the h. So now I'm just going to integrate the area to get the volume. 2 pi. Remember, for discs, it's pi's. For washers, it's pi. out in front. And then for the shell, it's 2 pi. 2 pi and then RH. So here we go, 5 minus y, and then the 4 minus y squared. That was a dy integration, and I'm accumulating all of those slices, starting with the bottom one, which was at 0, all the way to that top one. Remember, that was the coordinate point 4, 2. So it's from 0 up to 2. There would be the integral that represents the volume formed by this specific revolution. 2 pi RH, that's the formula that we're integrating. 2 pi RH. Conceptually, visualizing it is usually most of the work, most of the struggle, but hopefully it's getting okay. All right, let's clear that out, and then let's move it on to the next one. Here we go. It says find the volume of this solid generated by revolving the region around the y-axis. It says for A, we're going to use shells, and then for B, we're going to use discs. Instead of discs, it's actually going to end up being washers. Oh, well. All right, so that one's going to end up actually being washers. All right, let's do it. Let's do the shells. All right, let's graph the things first. Here we go. Let's go back to here. Y equals x squared. Okay, I can do that one. Y equals x squared. That's pretty good. And then we've got the other one, which is the cube root function, which looks like this. It's like the square root, but it's got the other side also. It's a little bit flatter, but there we go. So there's our region. Notice we don't really care about the branches to the left. We really only want that region that's in between the two. So here we go. There's our region, and then here's our region. Now the two intersection points, like what numbers can you square and can you cube root and get the same thing? Well, 0 and 1, right? So that intersection point's at the origin. That's also trivially obvious by just looking at the graphs. That's at the origin. What's the other intersection point going to be? Well, if you can square something and cube root it and get the same number, it's the point 1, 1. So the integration is going to be 0 to 1 either way. If it's a dx integral, it's going to be 0 to 1 that way. If it's a dy, 0 to 1 that way. But it's going to be a 0 to 1 integral either way we shake it out. Okay, now this one, it tells us to revolve it around, was it the y-axis? Okay, so here's my axis of revolution. Another one's going to be the same axis of revolution. But for that second one, it wants us to do washers. Okay, let's do the first one first, then we'll worry about the second one. Okay, if I want to do shells, remember shell, I need a parallel slice. So if my axis is vertical, that means I'm going to need a vertical slice, which means here, the shells is going to end up being dx. Okay, now let's revolve this thing. The top point is going to revolve around. The bottom point is going to revolve around. I've got that one kind of arbitrary cylindrical shell. That was a random xy point on the blue curve. This is another random xy point. Now those two things would have the same y values. Or sorry, definitely not the same y values. Those two things have the same x values, right? That one's just lower, that one's higher. So those x values at those two arbitrary points, those are the same. But we have the green y value, that's the one on the bottom, and then the blue y value, that's the one on the top. Okay, let's figure out what these dimensions are going to be. The height, it doesn't matter, the height and the radius. Let's go get the height first. There we go, there's the height. It'd be like that y minus this y, right? Y minus y, you're like, okay, 0? No, right? The h is like the s value that we've seen multiple times in this unit. It's the distance between those two functions. So it's going to be the top y minus the bottom y. So here the blue y was the cube root minus the green y, which was x squared. And I needed them to be in terms of x because this is a dx integral. So I started off as y minus y, but that doesn't cancel because they're actually two different y's. So the top y, blue, minus the bottom y, green. And then the radius, that's going to end up being the distance from that slice to my axis of revolution. That's my radius. And that radius is just x. That's pretty easy. Horizontal distance over from 0, that's x. And now we're ready to go. All right, we're ready. Let's integrate this sucker. Remember, for shells, it's 2 pi out in front. It's 0 to 1, but it's 0 to 1 this way. 0 to 1, and it's 2 pi r h, so x. And then I've got the cube root minus the parabola. There we go. Okay, now that integral, we could like multiply it out, we could integrate it, and we could leave it in terms of pi. That's great. But we're just going to math 9 it, and then we're going to get that the volume is 1.122. Right? Could we work it by hand? Yes. If we had to work it by hand, like really the integration would be fine, the plugging in would be fine. We would just have to leave it with a pi in the answer. But we're going to just leave it as the decimal. Okay, so we're going to use calculator, right? GDC, we're going to use the calculator to do ourselves the math 9. Could we do it by hand and leave it with a pi? Yes, but we're not going to. So there we go. We're done with the part A, which told us to do shells, which meant I had to do the dx, right? But it told me to do shells, and that shell method required a parallel slice, which meant I had to use dx. But that one's done. Now, the second part tells me to use washers, or really it tells me to use discs, but really it's got to be washers. And remember, those have to be perpendicular slices to my axis. Since the axis is vertical, perpendicular to it would be horizontal. So this one, since it requires washers, this is then going to require us the dy integral, right? If the shells is dx, then the washers will be dy, or vice versa. If the shells was dy, then the washers would be dx. One of them is the dx, and the other is the dy. They're like these two counterparts. One of them is kind of the dx integration, the other one is the dy. You can always do either. It just depends on which geometry formula you want to integrate. Pi r squared for a solid disk, more likely it's the washers with the whole pi, big R squared minus little r squared, or if you have the shells, it's 2 pi rh. Still integrate the area to get the volume. Just which area do you want to do? Shells versus washers, it's about the same level of difficulty. Here we go, let's revolve it. That inner point revolves around, creates the hole, the outside point revolves around, gets the outside edge. And so we need to identify what those two radii are, right? The big radius is always dealing with the farther away point. Remember, that's just a random xy point. So that big radius is x, but it's the x value on the green curve. So let's go take that green curve and let's solve it for x. If y equals x squared, that means x is going to be the root of y. Again, technically x would be plus or minus, but we don't care about the negative root of y because we don't really care about the left side. So there, that x value is going to end up being the root of y. You have to go to that equation and then solve it for x. No biggie. Might as well do the other one too while we're at it. Right here, if we have y equals the cube root of x, that means x is going to be y cubed. Okay, now let's go back and let's figure out what this little radius is. The little radius is the distance from the axis to the closer point. The little radius is also x, but it's the other x. Big radius was dealing with the farther point, which for us was the one on the green curve, so I needed the green x. And then the little radius is dealing with the closer point. What's that horizontal distance? X, but it's the x value for the blue curve, so it's going to be the x that equals y cubed. So visualizing it is kind of most of the battle, and then we just got to remember, integrate the area to get the volume. Here we go. Volume equals, pi goes out in front for disks and for washers, but it's pi big R squared minus little r squared. Remember, this was a dy integration, so it's really 0 to 1, but it's in that vertical direction. Still 0 to 1, though. And then there's the integral that you could set up. This one actually cleans up pretty well. So I could do 0 to 1, and I could do y minus y to the 6th. That would work, and that's really a very easy integral, like 1/2 y squared minus 1/7 x to the y to the 7th. And then plugging in 1 and 0 would be easy, and then you just leave it in terms of pi. We could do that by hand, right? And then we could just leave it in terms of pi. But again, either one of these two, come on. This thing's just not working very well. My allergies are killing me. Either one of those, we could use the calculator to math 9 it. We could do it by hand and leave it in terms of pi, but we're just going to math 9 it. And guess what? If we math 9 it, guess what answer you're going to get? 1.122. Let's think about why is that the same? Were they supposed to be the same? Yes. What changed? Nothing changed. It's the same graphs, right? It was the square root. Actually, it was the x squared, and then it was the cube root. It's the same two graphs, which means that yellow region was the same. How we build it right? Whether I build it by stacking the shells from the inside out, kind of like those concentric shells, or like the little like Russian dolls that nest inside of each other, whether I build it from the inside out with shells or whether I build it from the bottom to the top with washers, you're still going to end up with the same shape because you took the same region and you revolved it around the same axis of revolution. So whether you build it with the shells or with the washers, you're going to end up with the same 3D shape. Okay, so of course those final areas are going to match, but everything prior to that is probably going to look different. Like if we were to compare these, right, the integrals that you set up are different. The calculus that you would do if we solved it by hand would be different. Very likely that second to last step for each way would probably be different. But if we got it all to the final singular answer, then we would see that it's the same. Whether we use the dx method or the dy, one of them will be shells, the other one will be washers. There's like these two counterparts, these kind of two parallel tracks that will both get the volume done. Whether you do the shell or the washer, you're going to get the same 3D volume as long as nothing else changes. If any of the curves change or if the axis of revolution changes, well then yeah, you would have a different 3D shape. But if everything stays the same, then of course the volume should be the same. Okay, we're going to kind of end it on this video. There's one more page of examples we're going to do for area and volume, but I'm going to do that in the next one because I'm tired and I don't want to do it today. So we're going to end this video and then you can watch the next one.